let's take a look at the Plate Tectonics lab. And like all labs, you're going to get a handout that summarizes many of the things I talked about in lecture, like the driving forces of plate tectonics, the different types of plate boundaries, and what happens at those plate boundaries. Reminders of things like partial melting happens at about 150 kilometers deep, and magma rises to create volcanoes in these subduction zones. And then there's a few things that I hadn't introduced in lecture that I'd like to introduce now in lab. And one of those is this concept called the Wilson cycle, which is the opening and closing of an ocean basin. So in lecture, I talked about how supercontinents come together, right? All the continents come together, and then they break apart, and then eventually they all come back together again. And the Wilson cycle is part of this. As a supercontinent breaks apart, an ocean basin forms, it opens up, and then we have a nice big ocean, and then eventually that ocean closes back together and the supercontinent forms again. And there are some steps to this Wilson cycle. First, you have a continental rift forming. Then you have a narrow linear sea, like the Red Sea. Then that opens into a big ocean basin, and then eventually subduction starts and the ocean starts closing again, and then finally continents collide and a new supercontinent is formed. You will have one question in this lab on the Wilson cycle. Now, another big part of this lab is calculating plate movement. And when you calculate plate movement, you're going to do two things. You're going to calculate the direction and the velocity, how fast things are happening. So for calculating the direction, mantle plumes are really a good place to go for that. Mantle plumes are stationary, and those volcanoes that are created by the mantle plume will then create a path that shows you what direction the plate is moving in. And when you determine directions in geology, you don't just use north, south, east, west, you actually use something called an azimuth. And an azimuth is where we take basically north, south, east, west, but we divide that into degrees, basically 360 degrees. So north is 0, east is 90, south is 180, west is 270. This is why if you watch like movies like Top Gun and stuff, and Maverick in Top Gun is saying, hey, I'm flying bearing 090. Well, what he's saying is he's flying east. He's flying 090. So now you know what that means. So when you're telling me what direction the plate is moving in, don't just tell me it's moving east or it's moving northwest or something like that. Estimate for me what azimuth that plate is moving in. Now, when it comes to calculating the rate of plate motion, you use a very simple equation, and that is distance equals rate times time. So if you have a distance and you have a time, you can calculate that rate. And I will show you this using an example. All right, one other thing to remember in geology is since it is a science, we are going to be using metric. So we're going to be using centimeters, meters, kilometers for measurements. And then our ages in geology are measured either in thousands years, millions of years, or billions of years. So I promised I would give you an example of how to do this. So let's do this. Let's look at question number 1 here. So first of all, it says figure 1 shows the North Pacific and the distribution of the Hawaiian Island chain and the Emperor Seamount chain. The numbers indicate the age of each island in millions of years. So let's look at that. So here's our big example of the North Pacific. There's the Hawaiian Islands, there's the Emperor Seamounts. Now, if we look down here, here we have a close-up of the Hawaiian Islands. Now, question number 1 states, what was the rate of motion in centimeters per year in the Hawaii region from 4.7 MA to 1.6 MA? So let's just start with that part of the question. Well, if we look at, let's see, what do we have? 4.7 MA. Let's find right here, this volcano was erupting 4.7 million years ago. Okay? And this volcano, see how this arrow points there and it says 1.6? This volcano was erupting 1.7 million years ago. So remember, distance equals rate times time. We are given some times. We need, and we can measure a distance. Now we need a rate, and we can use that to calculate the rate. An easy way to measure a distance on a map is to take a piece of scrap paper like this. And see how I'm setting it down right here. There's my location 4.7 million years ago. Here's the volcano that was erupting 1.6 million years ago. So there's my distance. Now I bring it down to here. This is a scale, and I can set it next to the scale, and right there, that is 150 kilometers. And oh wow, look how convenient that is. That's another 150 kilometers. So we know then that the islands moved 300 kilometers in that amount of time. But we want to figure out the answer in centimeters per year. So we have to put that 300 kilometers into centimeters. The way to do that is to add 5 zeros to it. So that's how far it moved. So remember, distance equals rate times time. That's our distance. Now, there's our rate, which we want to calculate, and how much time do we have? Well, 4.7 to 1.6 is how long? 4.7 minus 1.6 is 3.1. So that's 3.1 million years. But again, we want this in years. So if you want to do 3.1 million years, to turn this into simple years, you move the decimal place over 6 spots. So this would be 1, 2, 3, 4, 5, 6. Fill these in with zeros, and that's how many years. All right, so how do we solve this then? We have to get rate, r by itself, so we divide each side by this number. Divide, so that's going to be 3, 4, 5. I can easily cancel out a bunch of these zeros. Let's see, 300 divided by 31 is going to be something close to 9.7, I think. Yay, I got it right. So 9.7, and that's going to be centimeters per year. So hopefully everyone saw how I did that. I apologize, my handwriting's kind of off because I'm writing upside down. So you're going to do the same thing for the next question, except that's looking at the rate from 1.6 million years ago to today. Well, 1.6 million years ago, today is time 0. So you don't even have to do any subtraction there. You just use 1.6 minus 0 is 1.6 million years. So that's how you're going to be calculating things like how fast plates are moving. Now, other questions in here. you're going to be looking at how fast seafloor spreading is happening. And for that, you're given this illustration and then a map on this page as well. This one is, this is the Mid-Atlantic Ridge, and this is the East Pacific Rise. So for this, what we're doing, for question 6, it says measure the distance between anomalies 2, 3, and 5 along the Garrett fracture zone in figure 2. And what the anomalies we're talking about, those are those magnetic anomalies. Remember, we talked about how sometimes the minerals are normal polarity and sometimes they're reversed. That's the anomalies we're talking about here, is the normal and reversed polarity. Now, in order to do this then, we're measuring the distance along the Garrett fracture zone, which is right here between anomalies 2, 3, and 5. So we're going to measure then from 2 on one side to 2 on the other, which would be here, right? 2 to 2. Again, take a handy piece of scrap paper, set it down like that, put a couple little marks on it, come over here to our scale, and you can see, all right, that is going to be about, there's 0, that's 500, so 100, 200, 300 kilometers. And then you will just write that down here. And then you'll do the same thing, measuring from 3 to 3 and 5 to 5, and enter those in the chart down there. You will do the same thing for the Mid-Atlantic Ridge, and then you will plot some information on this chart right here, and you will use that to help you figure out which location has faster seafloor spreading occurring. This is fairly self-explanatory. You're simply plotting the depth of different earthquakes. This activity here is kind of fun because you're going to figure out how fast movement is occurring on the San Andreas Fault. So figure 8 here shows 2 outcrops of Miocene rocks, and those are right here and right here. They're labeled M for Miocene, and those are about 15 million years old. So what you're going to do is figure out, remember, distance equals rate times time, and you're going to be solving for the rate. Since we know these are 15 million years old, we now need a distance to get the rate, because these rocks were originally together and they have moved apart like this over the past 15 million years. So you have to measure the distance that they moved. And the best way to do that is think about how these were lined up when they formed and how they've been split apart. So you will want to measure from the top of this one to the top of that one, and that is the distance they have moved over 15 million years. So there's your distance. 15 million is your time. You can calculate a rate from that. Then, using that rate that you calculated, you're going to tell me when Los Angeles and San Francisco are going to meet because they're moving along the fault. So in this case, you're going to measure the distance between those two cities using the scale that's right down here. You just calculated the rate, and then you will be able to figure out the time. It's not going to be anytime soon. All right, these last questions all refer to this map right here. And you are going to be asked, what direction is the North American plate moving? And well, remember, direction is easy to calculate if you have a mantle plume. And guess what? We have the Yellowstone hotspot right out here. And so you can use that to help you calculate the direction North America is moving. You will also use that to figure out the how fast the plate is moving. And it says over the past 11 million years, well, right here you have a volcano that erupted 11 million years ago, and you can just assume that here is where the Yellowstone hotspot is today. So that will be the distance that you measure. Here is your scale. Do remember to use the kilometers and not the miles. So in any case, you're going to take a look at that. You're also going to take a look at what's happening out here. Now, right here, this red line, that's the boundary between North America and a small ocean plate called the Juan de Fuca plate. And so there's going to be a few questions where you have to look here at that Juan de Fuca plate to answer those. Then the last questions that you're going to see, remember I said you're going to take a look at the Wilson cycle. These questions here show cross sections of plate boundaries. The black shows ocean material, the colorless shows continental material. And you're going to tell me, remember there's those 5 steps, right? 1, 2, 3, 4, 5. You're going to tell me which of these cross sections represents the first step, which is the second step, and so on. Then down here, you're going to find me places on Earth today that correspond to each of those steps. Like, where do we have a rift today? Where do we have a narrow sea today? Where do we have a big ocean basin today? And you're going to put those in there, and you're going to be able to say, okay, let's have an obvious one. The East African rift is a rift. Well, which one of these diagrams represents a rift? Now, again, I know it's a lab. I know it's tough to do these things on your own. Normally, we'd be doing them in a lab together. I'd be walking around and giving you guys instant feedback. I'm sorry I can't do that. But, you know, if you have questions or you're having some problems, please contact me so I can help you with those.